Hello, this is Amy Thompson, CCAT's Chief Talent and Training Officer. I'm very excited to introduce this demonstration to you that demonstrates automatic workflow for coordinated measurement machines, CMMs. What you're going to see is how you can use that valuable digital thread and model-based definition data to speed up the programming of CMM machines. When I was a professor, I used to train students how to program these machines manually, and it took hours. Now you can actually use that data to program your CMM machine with one button press. And here's the demonstration from our CCAT team.
Hi, I'm Nasir Mannan. I'm the Principal Engineer here at the Connecticut Center for Advanced Technology. Today, we're going to be looking at how to use model-based definition to automate CMM programming. Here with me today is Chris Miller, an expert at CMM programming.
Thanks, Nasir. So diving right in, I have my model open here. As we can see, there's a lot of PMI assigned to the features. This is semantic information that can be read to generate things such as a CMM profile. So now that I have my model open, the first step I'm going to do is to go into the inspection environment. So clicking on File New, I have this dialog that opens up, this pop-up window. You're going to want to click on the Inspection tab. In this example, I'm going to want to click the DMIS General Setup. Typically, a site would take the time to define your environment, so you'd set up your CMM equipment. That includes the probe that you're going to use, any fixturing that you might use as well, and that's going to be an option that you'd have on this list here.
I see. So right now, you're just picking one of the generic templates that comes with Siemens NX.
Exactly.
Okay.
Right. And then, like typical NX, you're going to just choose your file locations and click OK. Great. So now I'm in the inspection environment. So my first step is to import the specific equipment that I'm going to be using. So I have three buttons that I want to just point out right here. My first being the program order view, the second being the machine view, and my last being the method view. So within the machine view, I'm going to double click on generic machine and specifically specify which piece of equipment we're going to use. So I'm going to go into CMM here, and for this example, I will choose the Winzo 3-axis gantry CMM. So a pop-up will come asking if I want to use the assembly positioning or use part mount junction. For this example, since it's a flat bottom part, I'm okay laying it on the granite table. Okay. I'm going to click OK, that option. We have an information window that shows that everything was imported successfully and that we have some pockets that have been assigned to the tool rack in which that we can assign specific probes to. Now that I have the equipment imported, I'm going to choose the head that the probe will sit on. So I'm going to click on head. In this example, I'll choose the Revo. And I will choose my probe. I'm going to switch from inch to millimeter since most of our probes are in millimeter. And I will choose this probe right here. Great, so I'll click OK. All that information has been imported. Just to show you, I can expand these windows here and show the probe mounted onto the head. So I'll go ahead and collapse all that. So we have the environment set up in which the part will be inspected. The next thing I want to do is click on Link to PMI in the ribbon here. This will just allow the kinematics to understand how the part will be inspected based on the geometry that's existing on the part. This window pops up here, so I have an option here to create paths, yes or no. I'm going to go ahead and click yes, just allow everything to generate ahead of time and then make my customizations later.
I see. So this is really the window that allows you to, with a single button click, identify all the features on the part, identify what tolerances are associated, and then have the software automatically create the program.
Right, yeah, so I would have a complete profile after clicking OK. So now I have a pop-up that shows me all the PMI that has been imported correctly. Sometimes you may see things that will be imported but not linked successfully, or things that are just not recognized at all. Yep. Typically what that means is your PMI is incorrect and needs to just be updated to the right format so that it can be read. Yep. So in this case, again, we have everything successfully read. I'm going to go into the method view right here, which will show me the geometries that can be inspected. These plus buttons here just show the features that were recognized by linking the PMI, and it will show the paths that were generated based off of that information.
I see. So these are your generic methods for the feature type. Correct. And then through the link PMI, it's identified all of these planes that are associated with that particular method.
That's correct. Yeah, so you may have a part in real practice that may need different inspection criteria or methods based on the feature, purpose. Yeah. For example, I'm going to create a new method, say for the cylinders. So I'll click on the method button here on the ribbon. I will choose the appropriate icon, in this case, inspection cylinder, and I want to assign it to the method itself. And I can rename it, let's say, tight tolerance. Perfect. So now that I created a new method and I defined it as a cylinder, These are the default settings that are associated with the cylinder. In this case, it chooses point set, but I want to choose a scan helix. When I choose scan helix, the following information can be edited. It's different information, and I can customize it how I would like it. As an example, you may want to have 4 or 5 or 6 rows inspected for that helical motion.
I see.
Maybe you only need 2,
Yep.
depending on the depth of the hole. But this is where I can go ahead and customize that. There may be something such as I want a zigzag versus a zag formation to be inspected. There's a lot of options here that you can customize to inspect that feature exactly how you want.
I see. So this is really the dialogue that you get to actually, this is your way of teaching the software that strategy that you would want it to use when you're using that particular method.
Exactly. And the nice thing is once I have this generated, I can easily import this later on. Yep. And then it's just a matter of the programmer needing to specify which features need to be dropped into that bucket, or in this case, this method.
Yep.
So I'm going to expand my cylinders here, and I will choose cylinder 18 as an example. I'm going to drag and drop that cylinder into that method. Likewise, I'm going to take the associated path and drag that as well into that method. And now I've associated that with a new inspection method. Once I finish with that, I want to resequence my path. So I'm going to drop that down. I need to go to my program order view, and I need to make sure that I'm on inspection paths. So here's my inspection paths. I'll move over to this ribbon again, click on the resequence paths, and here I have the option to prioritize how I want the path to be resequenced. A lot of times we'll choose distance of the path just to shorten up the inspection profile. Maybe you have a tool change that needs to be prioritized, maybe a heading will change. Here's your options. I'm going just for now to choose distance of path and click OK. And in a matter of seconds, it's regenerated that path.
Wow.
To follow that up, I want to make sure that there's no collisions during the process. So I will click on this collision avoidance tab right here on the ribbon. And I'm going to specify a plane, a safety plane. So if I can just zoom into my model here some. I know that this is my highest point on the part, and maybe I want my probe angles to happen a couple inches above that plane just to avoid any potential collisions. To be conservative, I'm going to stick with that 2 inches, but maybe in reality you might have a half inch or something like this. Again, it's a kind of a user preference at this point. So I'll click OK. It has created that plane as a safety plane, and I'm going to click OK again. And it's going to perform an analysis on the part and regenerate all that and add in some move points, some transition points, things of that nature, just to avoid any potential collisions.
I see. So at this point, it's actually generating the path that the probe has, that the CMM has to go through, move that probe into the position to be able to measure that.
Exactly. Okay, great. Now that we've run through the collision avoidance function, it has given us a report showing all the transition points and the new move points that the probe will sit so it can avoid any kind of collisions. Okay, so just as a quick overview, we have set up our CMM environment. Typically, the user would go ahead and just pull that out as a template and open that up, but in this case, we have created one from scratch. The next thing we did is we linked the PMI, so the model is now being recognized and all the PMI that's associated with those features has been read. Now the kinematics of the model know how to approach that feature and to inspect it. We have defined new inspection methods depending on the use case of that feature or that geometry. We've recategorized it, and in essence, we need to resequence that so it has a continuous flow. And the last step that we want to do before post-processing is just the collision avoidance, which we saw here. So now I can go ahead and post-process it, but just to show you what we have produced out of those few steps right there, I will click Simulate Machine on the ribbon here. A dialog comes up asking if I would like to adjust the speed and such. I'm going to enter the simulation settings option right here. There's a checkbox to check for collision. This will stop the process and show me exactly where that collision occurs. So if I need to make a last minute change or if there's something that's wrong, we can address it then. So I'll click OK. I have the speed set to 7 out of 10 just for our demonstrations. And in a moment, we will see the Z slide approaching the part and we'll begin its inspection. So I can go ahead and zoom in on that some just to show what the probe is doing. It looks like it's inspecting the smaller hole features on top there now. It's changing the probe angle and going to do that 2 inches above the part as we specified earlier before. For our simulations, I can go ahead and just pick up this speed a little bit. We Opted to see any collisions that may occur. Here we can see the orange Z-slide. That indicates that there is something with the Z-slide that has collided. It looks like from this view that the head is making contact with the granite, which is something that we can address afterwards, but I'm going to follow through with the entire inspection. And great, that's our simulation.
Awesome. So great, thanks for showing that simulation. Looks like just a few mouse clicks and you're at the point of generating a program, being able to simulate it. What's the next step after that?
Yeah, so the last step, Nasir, we're going to post-process this. I will choose the specific post-processor that I'm using. In my case, I want a DMIS 5.2, and I'm happy with that output file location, so I will click OK here. And with a matter of seconds, I can see my entire CMM profile listed right here. And following up with this, I would want to connect this directly to my machine and run my profile. Yeah, and to your point, a matter of a few mouse clicks, and that's us setting up an entire environment from scratch. Generally you're going to be able to do this in fewer clicks. Normally you just be able to select that one environment from our template, and there's a few mouse clicks that you have to perform. Make sure you're happy with the optimization and run it from there. So now that we've verified that there is no collisions in the CMM profile, I want to now post-process this to my machine so that we can begin the inspection. So I'm going to open up this dialog here, click on DMIS 5.2 for my specific example. My output file is correct and click OK.
And that's because you chose a DMIS template.
Correct.
At the beginning.
Correct. So here we can see all the steps that are involved to inspect this part. And again, my last step is to push this to my machine and begin the inspection.
Very, very straightforward. Not very difficult to use at all. I mean, it looks like there's no programming at all. You're literally just clicking some buttons. You're setting up some methods, assigning features to those methods. And it looks like, for all intents and purposes, I don't have to click physically on the model. The software seems to pick up on all the different features. It seems to pick up on all the PMI. It's taking care of a lot of that manual work for me. This is fantastic technology.
And this here, your biggest challenge is just categorizing your features into the right bucket, the right inspection method. Wow. So as a programmer, that's the biggest challenge you'll have. And other than that, it's a few clicks in.
Great.
Yeah.
Thank you for joining us on this video series that really shows you how you can leverage model-based definition to streamline manufacturing processes.
So you can learn how to implement digital thread practice by taking this practice from design to manufacturing to QA in our hands-on computing and our hands-on automation nexus. You can learn how to implement this model-based definition and digital thread practice in our digital thread training lab on the third week of every month during digital quality assurance and inspection week. So come participate.